Chemistry time. Let's talk about covalent naming. You remember naming ionic compounds, right?
No.
Oh, golly. You should remember ionic naming, right? We said things like sodium chloride, right? We changed the ending of the anion to say "ide." Otherwise, we just said what they're both called, with the exception of transition metals. And then when we wrote their formulas, we had to make sure that the charges matched. Which for ionic compounds that was fine. Their charges matched. For covalent compounds, as we'll see, we do it in a little bit different way. But it's still, this one's actually, I think, more fun. The first thing we're going to talk about is, and you can turn with me on to page 248 if you want, but we're going to talk about, I'm going to write all this on the board so you don't have to be with me on that page if you don't want, but you can follow along if you do. So, the first thing we're going to talk about is, and we even just saw this in the video, but we have to have memorized these Greek prefixes for the numbers. So mono, you're going to have a little table here. So mono means what? 1. Di.
2.
I don't know why I've changed my handwriting all of a sudden.
Non-existent. Die.
No. Di is 2. Tri.
Ooh, 3.
Tetra.
4.
You're seeing a pattern here. Penta.
No, I'm just smart. 5.
I think it's hexa.
6.
Yeah. Hepta.
7.
Octa.
8. Wait, what's 4 again?
Nona.
Tetra. How do you spell that?
Nona, it should be. Nona is 9, and deca is 10. There are more. It's quite rare to have compounds that have more than 10, and even like these from hexa on down are fairly rare to begin with, but we need to have these memorized. What are some little things that we can remember?
7.
Like what are hepta? What are some things that we can remember? Many of these are also the names of the polygons or the polyhedra, right? So like if we have a hexagon, that we know from geometry or from 7th grade math that is a 6-sided polygon, right? Octagon, an 8-sided polygon. Decagon, 10-sided polygon, etc. Where they kind of break down from that pentagon. I mean, those are fairly easy. These ones not quite as much, but you might have them memorized. What's mono? How can we remember that mono is 1?
Because it's only healthy if you get mono once.
Sure, whatever. So you're referring to mono when we talk about mono. The kissing disease.
Ah, no, I've had that in like 2nd grade.
The kissing disease.
So
We talk about what that's short for. Mono. Mono is.
I was a player in
What?
2nd grade.
2nd grade? Good grief! You better keep it together. Mono is short for mononucleosis, which means that this particular organism that causes this disease has one nucleus. It's an inflammation, osis. Maybe itis is inflammation. It's a disease, osis, caused by an organism with one nucleus, mononucleosis. We have one nucleus too, but that's what that organism happens to be called. What?
And mono, isn't that when you're like spleen
Yeah, your spleen can rupture, but that's not what this class is about. Mono meaning mononucleus. What's another reason we ever see mono in our lives? Monopoly. Yeah, that's really good. I've never actually thought of that. Yeah, monopoly it comes from the Greek words for one and polis, which is city, but it's when one company controls all of one kind of good, right? Like you've heard about in history in the Gilded Age in America, when there was a monopoly, when Standard Oil had a monopoly on oil. You could not buy oil anywhere worldwide except for from Standard Oil. So they could make it, and the problem with a monopoly, please let me speak. The problem with a monopoly in economics is that group or that person can charge whatever they want for that good, and people who want that have to own it. Are you listening? Okay. So mono, when else do we see mono?
Shh. There's one that's really bothering me that I can't think of.
I see mono when when you change the settings of your television or headphones or something. To have mono sound means it's as opposed to stereo sound. Stereo means that there's going to be a different channel for left to right. So like whatever the artist or movie sound designer has chosen to be coming out of the left speaker will come out of the left, and out of the right will come out of the right. But if you have it set to mono, it'll be the same out of both, right? And mono is better in some cases. Like for instance, yeah. In fact, if you want to test your headphones, they have like all these videos on YouTube about stereo headphone tests where you can tell how good your stereo headphones are. But if you're only if you're only going to listen to the one earpiece because you got to pretend to pay attention in class, for instance, have it set to mono, and then both channels will come through that. And you can really notice it, especially I find.
I wonder if that's why some phones, struggle.
Yeah, maybe. Yeah, some headphones. But like I noticed this. I don't like the Beatles, but I noticed this a lot in some Beatles songs. They're really really channeled, and so if you're only listening to the one headphone when you're listening to a Beatles song, a lot of times it'll just sound like the drums. Like it'll just be the drums. And through the other headphone will be everything else, the vocals and bass and guitar and everything. It'll just be drums through one and all that through another, and that's called sound mixing. Anyway, mono means one. Di. What kind of things do we see that have di in them? Dice. I don't know that that's related. I don't actually know where that word comes from, but maybe. Die something. Die.
You want to die? Die.
Probably not. Okay, just try to remember that die is two. I guess we don't have any good mnemonic for that.
Stop. We have to. It won't be fun if we don't.
There's only two letters. Die, two.
That's a good mnemonic. Yeah, this is the only one that only has two. Tri is easy. Triceratops has three horns. Tricycle has three, right? Tetra, this one people sometimes struggle with because these two start with the same letter, but I tell you, Tetra is easy because if you've ever heard of a game called Tetris, all the little, what are called Tetrises, I don't actually know, they all have four little lumpies in them.
If you try to make a match together.
Yeah, they all have four little...
Don't forget that really hard one.
Oh, which one's the really hard one? Oh, the stupid Z one?
Yes.
That idiot. We hate him.
We don't like him. He can go
yeah, so all these tetroids, I don't know, all these tetragons, right, they all have four little nuggets. Okay, so anyway, we have to have these memorized. We have to, because, and I find this, in my opinion, covalent bonding naming is easier than ionic because we don't really have to worry about the charges. We just call it based on what it is. So like if it says P3O5, we would write tri-phosphorus pentoxide. If this happens a lot with oxygen, and you should write this down. Hey, could you please write down the example? If the word that we're going to put with our prefix begins with a vowel, we remove the vowel from the ending of the prefix. So instead of being pentaoxide, it's pentoxide. Triphosphorus pentoxide.
Are you going to give us worksheets to work on?
Oh yes. Oh, you better believe it. What about this one?
Nitrogen, and that one's difluoride.
Remember, it's fluoride, but yeah, difluoride. Now here's the thing. Mono is not always used. In fact, we quite infrequently use mono. Write down somewhere that the only time we use mono is to differentiate between a more common other substance. Mono is used to differentiate when another substance is more common. So for instance, I'm going to give you an example. Name this one. Based on our naming. What's C? Okay.
Carbon oxide.
Try again. Carbon what?
Dioxide.
Dioxide. So then, in this case, we call this one... Nope. Just carbon still, but carbon monoxide, right? We call it monoxide to differentiate because carbon dioxide is more common. So if this didn't exist, which it does, it's very important, but if this didn't exist, we might just call this carbon oxide. I forgot to switch this to picture-in-picture. Oh, it is already in picture-in-picture. So carbon dioxide, carbon monoxide. So then it should be, in my opinion at least, once again, it should be even easier to go the other direction. All we should do is just look up what the symbol is. So for instance, if we, I guess I'm on page 251. Let's look at 251, page, or number 25. It says silver, oh, what? That's an ionic compound. Let's do 26. Dihydrogen oxide. So what's dihydrogen?
Can you say it again?
H2? Oh. Let me tell you, 26 is wrong. This is not called dihydrogen oxide. What is this called?
256?
Water. Yeah. 251. Water. This is called water. Now here, I'm going to give you two other examples of this that you have to have memorized. This one, we do not call this dihydrogen oxide or dihydrogen monoxide. That is wrong. We call it water. If you put dihydrogen oxide because you think you're being funny, wrong. You're going to get a point taken off. It's not funny, it's just wrong. Water is correct. So
like, what if you put like water underneath it? Just to be funny.
Still
and then
wrong.
you're like,
Still
then
wrong.
you're like,
Because I hate when people try to
they
come.
put water.
Oh,
they're
okay.
not.
So the other one you need to know is this one. NH3 is called ammonia. Not to be confused with your polyatomic ion, NH4, 1 plus, which was ammonium. This one is ammonia, NH3.
And what's the thing for it?
NH3, ammonia. So in the same way, we don't call this nitrogen trihydride. Wrong. We call it ammonia. And then the last one, and there are lots of these. This one is the one that comes up both on your chapter review and on your test. But this one is called methane, and that's because this uses organic chemistry naming conventions. So there are literally millions. Organic chemistry has hundreds more rules of naming, and there are literally more organic compounds. That is a compound that has both hydrogen and carbon than there are inorganic compounds. But this one this is one example of an organic compound, and we use its organic name methane, as opposed to saying carbon tetrahydride. Okay? You think you're good on covalent naming? Let's do a couple more practice problems just to be sure. I think you are, but let's look at SO2. SO2, help me name it. Jasmine, what should I call it?
Sulfur dioxide.
Yep, sulfur dioxide. Let's do this one next. Sulfur Tylene trioxide.
You want the equation?
Well, I want the formula.
SO3.
Good. So that's really, as long as you have this memorized, that's as difficult as covalent ones get. I mean, the numbers get higher, but it's just another different prefix. Just be sure that if the second word, like oxide, because of the vowel, you remove the vowel from the end of this one. So you don't ever call it heptaoxide, it's heptoxide. Let's move on to the next thing. This is also, now we're going to do, it's still covalent naming. Well, it's kind of both covalent and ionic naming. They're bonded together ionically. But anyway, we're going to move on to another thing, which you're going to label acid naming.
Acid naming.
Acid naming. So the first thing we're going to do is talk about just a real quick rundown on what an acid and a base, what those things are. So write down acid naming, and then the first thing we're going to do is define acids and bases. So an acid, we're going to use what's called the Bronsted-Lowry definition of an acid, which is the easiest. But an acid is a substance. You writing this? So you're writing something. That's good. Acid naming. So an acid is a substance. Have you ever heard of an acid before?
Yeah.
What's an acid? Where have you heard the word acid before?
My dad likes to say that's asinine.
Asinine is not acid. Well, what is acid? Where have you heard the word acid before? Asinine just means stupid. Acidity. Yeah, well, where have we heard? What kind of acids are there?
The kinds you're not supposed to put in your body.
Do you have acids already in your body?
Yes.
Of course you do. What kind of acid is already in your body?
Like your
Stomach acid. Your stomach has acid in it. Lemon juice is an acid. Vinegar is an acid. We use acids in the lab all the time. What do vinegar and lemon juice have in common?
They don't taste very good.
They both taste excellent, but what do they taste like? They have what taste? Sour. Acids are sour. You could write that down. That's not the definition.
apple cider vinegar.
Acid
Yep.
is a substance.
An acid is an acid. Let's put that. An acid is a substance that releases hydrogen ions, H+, in aqueous solution. We're going to talk about what aqueous solution is too. First of all, hydrogen ion meaning what?
And what's that one word?
Aqueous?
Can you spell those?
AQUEOUS.
EOUS.
Okay, so what's a hydrogen ion going to look like? Well, first of all, let's draw a hydrogen atom. What's a hydrogen atom got? One what? One proton and one electron. We'll assume it's just hydrogen 1. One proton, one electron. What if it's a hydrogen ion, H+? Be careful before you answer. Think about it before you answer. What's it going to look like? Hydrogen plus. What does it have to do to get a positive charge? So what's it going to look like? Just the proton. So sometimes, in this definition, acids are even called proton donors, because all a hydrogen ion is just a proton. just a proton. Anyway, if a substance does this when it's in aqueous solution, what do you think the root word of this is? Aqueous. Water. What do you think solution means? It's mixed together, right? So if this is mixed with water, basically, this is the same as a water solution. If an acid is something that when it's mixed with water, it generates hydrogen ions. And your body has specific receptors for those hydrogen ions that make it taste sour. That's why it tastes sour. The sour receptors on your tongue, all they do is bond with a hydrogen ion, and when they do that, it sends a nerve signal to your brain saying, sour. Yes, what?
So like, the malic acid?
I'm sorry, what?
The malic acid?
Yeah, malic acid. Where have you seen malic acid before? Yeah. They're your Sour Patch Kids. You guys are weirdos. You probably love Sour Patch Kids. Those things are covered in malic acid. That's why, if you ever had a mega warhead, the difference between a mega warhead and a... I'm going to tell you if you could just stop interrupting me. The only difference between a mega warhead and a Sour Patch Kid is that on a mega warhead, the malic acid is powdered a lot finer, so it has a greater surface area. You remember from earth science, has a greater surface area, so it can combine with more of the hydrogen receptors on your tongue at once, which makes it seem sourer. What happens? Mega warheads even have a warning on them that say what?
Sour.
Sour? No, they say what? Have you ever?
Too many, you're gonna die.
Don't eat too much, it says, or it'll tear up your mouth. It says it more professional than that. But basically, you'll get acid burns on the roof of your mouth and your tongue that will make you bleed, because that's what acids do.
I've got those from Sour Patch Kids.
Yeah, you probably have, because you eat buckets upon buckets of Sour Patch Kids, which is a bad choice.
Like,
Anyway,
like
so an acid generates these ions. This makes it, write this down. Acids are reactive. Because it has generated these free ions, they are reactive. That's why they hurt you, right? That's why they if you get a concentrated acid, even on like your finger, it will make you bleed. It will destroy your flesh because it reacts with the cells that make you up, and it wrecks them, which will make a hole in you, which will make blood come out of you because you're full of blood. Anyway, a base, the other thing, a base is a substance that releases hydroxide. You already know what hydroxide is. Hydroxide ions in aqueous solution.
In what?
Aqueous solution, which we already know what it is. And what's a hydroxide ion? OH -1. Okay, so now two things. I think this is cool. What is, if, just as kind of a side note, I mean, we'll talk more about this in the future, but if we add this, H plus, to this, OH minus, what do we get? H plus OH minus yields what? Just write it out. What will the charges do? Cancel out, so we'll have no charge. What will the formula be? HOH. Write this in a different way.
H squared.
No, come on. H2O. What is it?
Water.
So if we have a Bronsted-Lowry definition of an acid and a Bronsted-Lowry definition of a base, when they combine, they always release water. Anyway, just like the acids, bases, I'm going to erase that because that's an anyway. Just like the acids, these are very reactive. In fact, these are probably, for a given concentration, like a given strength, these are probably worse for you because what happens is when these bases react with fat, they form soap. So basically the lipid bilayer, you know about lipid bilayer? That makes up, like animal cells have a cell membrane, right? You're with me so far. That cell membrane is made out of a phospholipid bilayer, right? You were with me there? Mm-hmm. And the lipids are fats. So basically what you are made of is little blobs of fat with some water inside of them that do a special job. But those little blobs of fat, if this touches them, that turns your cell membranes into soap, which, number one, that's not going to work anymore. Those cells are dead forever. And number two, it makes it feel slippery. So if you get a base on your finger, it makes your skin cells turn into soap, and that makes it like, oh, slippery, have fun. But it's also very bad for you. If this gets in your eyeball, you're blind forever. Like literally forever, because it'll ruin the cells in your eye, and it'll...
Well, you could get an eye transplant.
Nah, I mean maybe, but probably
you
not.
get those little glass eyes that you always see people plugging in.
But you're still blind. Okay, anyway, so...
But the people don't know that about you because you're not just going to
So you're going to do something.
An acid tastes sour in solutions, right? They're both dangerous, but an acid tastes sour in solution and it releases these hydrogen ions. A base happens to taste bitter, but only because our bodies detect the soap and that's bitter. So if you were to, and don't, but if you were to accidentally ingest a base, it would taste soapy because it would turn your mouth cells into soap, and then when you swallow, you're like, soap.
And then you die?
In fact, this is how, not always, but try not to do that anyway. This is how soap is actually still made. Like bars of soap are still made, usually now with fats that are either generated in like a petroleum mine. But it used to be. In fact, the Army Survival Guide still tells you, here's how you make soap in the wild. Kill an animal, render its fat, like just melt all of its fat down, put in some ashes from a fire, which has bases in it, and that makes soap, and you can wash yourself with that's called tallow soap. Anyway.
My neighbor was like Amish.
What?
How does it not break down your skin?
Because once it reacts with the fat in the animal fat, then it becomes soap instead of being this. So basically, this is sometimes called lye. Well, a particular base is sometimes called lye. Anyway, all of that, these we just name like normal ionic bonding rules. So for instance, if we had this, NaOH, we would just call that sodium, which is Na, hydroxide. Those ones are easy. The bases we just name like normal ionic compounds.
See, like, okay, but the one above where you're making soap, does it smell bad? Because I had this Amish girl that worked with me. She used to try to sell us her soap, and it smelled so bad.
Why might the soap smell bad if they're making it in the traditional way?
It's made of animal
It's made of animal fat, so it's going to smell like animal. So generally, that's why people started putting scent. That's why you have scented soap now.
Yeah,
because in the
she,
olden
like-
days, they put scents in it so that it wouldn't smell like that anymore.
Butter, organic soap. And we'd be like, no, thank you. And then she'd be like, smell it. And you'd be like, it smells so good.
My mother-in-law makes soap out of goat's milk. Looks like milk is fatty. Anyway, I don't think that smells particularly good either. The scents she puts in it smell good, but the goat smells like goat. Anyway,
Aw.
so we just named these as normal ionic naming. So sodium hydroxide, if we had something like this, what would we name that?
potassium hydroxide.
There you go. Potassium hydroxide. You should be able to recognize that bases end in this hydroxide. They have this little hydroxide on them. You should be able to recognize, like if you see this, you say, oh, that's a base. This one, sodium hydroxide, is what we call lye. If you've ever used ammonium or ammonia cleaner on your windows, that's ammonium hydroxide, and you know what that smells like. Okay, whatever. So now we're going to name the acids, and this is just a little bit more, complex. So
That's how you name the acid.
that's how you name the bases. How we're going to name the acids is a little bit different. It's not hugely different, but just follow along and you'll be okay. So naming acids, that's what we got this, right? Acid naming. So acids are always going to have a hydrogen ion on the front. So first of all, how do you recognize an acid if you just are given the formula? Well, first, it's going to always have a hydrogen or more, right? So for instance, if we have this, HCl,
That's an acid.
that's an acid because it has a hydrogen out here front. What if we had this, H2SO4? That's also an acid because it has a hydrogen out front. This is not the only definition of acids, but this is the one we're using for now. They have to have this hydrogen out front. Acids have the hydrogen out front. Bases have a hydroxide in the caboose. So how do we name these then? Well, like I said, it's a little bit more complicated. If the anion, what's the anion? The what one? The negative one. Where do we find it? No, I mean, where do we find it in this? Which one of these things is the anion?
The second one.
Yeah, the second one. Remember, the anions always go second. What's the cation always going to be in these? The first one, but it's always going to be what? Because it's
Hydrogen.
Yeah, it's always going to be hydrogen. So if the anion is monatomic, we name it hydro something ic acid.
Wait, say that again?
If the anion is monatomic, what's that mean? Only one atom. We name it hydro, whatever the atom is, ic acid. So this one becomes hydrochloric acid.
Well, okay, I like that.
Okay, that one's good.
What if it isn't?
If the... Well, I should have phrased that differently. I'm sorry. If the anion... Let's change it to this. Do you have an eraser? If the anion, let's put this, isn't an oxyacid, anion.
Wait, what?
We're going to talk about that in a
Changing
second.
our definition?
Yeah, we are. Just erase it, because this will be better.
Ew.
I like that, she said, and now she doesn't. If the anion isn't an oxyanion, that means if there isn't oxygen in it,
So, if it doesn't have oxygen,
basically. But do write the word oxyanion.
if it doesn't have a...
Oxyanion. Then it's hydro, whatever, ic acid. If the anion, what do you guess this is going to say?
has an oxide.
Well, we're going to say is an oxyanion. We name it ic. Oh, sorry. We name it, if the oxyanion was ite, we change that to us. And if it was ate, we change it to ic. And then we add acid.
8,
Yeah, so for instance, what kind of oxyanion?
Ite goes into what?
Us, O-U-S.
And 8 goes into IC.
Yep. So, what's this?
Hydrogen,
Well, don't try to name it yet. What's this?
sulfate.
Sulfate. So 8 becomes ic. So we call this sulfuric acid. There's no hydro. The hydro only happens if it isn't an oxyanion.
Oh, man.
Sulfuric acid. So the 8's turn to ic, the ites turn to us, and we always add the word acid. There's a flow chart on page 252. Oh golly, the flow chart doesn't help. Forget about the flow chart. There are some. Look at it instead. The table on page 250. It says naming oxyacids. We have there HClO3. Look at that. Where's your book? Turn your book to page 250 and look at HClO3. It says. What polyatomic ion is in there? ClO3 minus. What is that? Chlorate. So we change it to it. So it becomes chloric acid. HClO2 becomes chlorous acid. HNO3 becomes nitric acid. And HNO2 becomes nitrous acid.
Oh my
Okay,
gosh.
they just, if the thing it was made out of ended in ite, we change that to us and add acid. If it ended in ate, we change it to ic and add acid. If we're going the other direction, for instance, if I write down acetic acid, well, this ic came from what? Ate. So what would this have been? What polyatomic ion is it? Acetate. So then we combine acetate. What's the acetate polyatomic ion? C2H3O2 with enough hydrogens to make it happy. What's the charge on this? Negative what? Sorry.
1.
Negative 1. So how many hydrogens is it going to take to make it happy? Try again. Just 1, right? Because hydrogen is only 1 plus. So then it becomes HC2H3O2. Or let's do this one.
Oh my gosh.
Hydro bromic acid. So when we see the hydro, what does that mean? The anion was what?
It's an acid.
Okay, we know it's an acid, yeah, but when we see hydro, it means that the anion was what? Go back up here. If the anion isn't an oxyanion. So, was this an oxyanion? No. So what must it be? It's just HBr. It's just from the bromine ion.
Can we do one with where it is in oxy?
Okay, yeah, so let's do, I'm trying to think of one that we haven't already done. Because we just read several from the book. Sulfurous acid. Well, what's the us ending mean? It was, no?
It was ite.
Ite. So us comes from ite. So what polyatomic ion must this have
It
been?
was sulfite.
Sulfite, which is,
S-O...
no, that's sulfate. So SO3. And what's the charge on it? Negative 2. So how many hydrogens is it going to take to make it happy? 2. So H2SO3. Naming covalent compounds is easy, right? We just say what it is and tell how many there are of each. And the reverse is true for when we go from name to formula. We just write down whatever it says. This is a little bit more difficult, or not, I wouldn't say difficult. It's just going to take some more getting used to because it's a little bit more involved. There are several steps we have to follow and remember. Do you have questions about this?
No.
Okay, we'll need to do some more practice, but you will get it. Bye. You're a